1 2 1 2 1 2 1 2 1 2. Woo! Now let's go through this lower common ancestor operation and see how it applies, right? So let's go in. So we go into it. So we see our two values. We are looking at D and at E, and let's see how it changes, right? So we will point to our current. This should take us to the none. We see that our current is the root, and we point to this guy. Now we go to the current, and then we step into it. Now the real dance begins. Now I will see you could see that now it mimics the one outside of the function and returns it as none because we are talking about the non-local. It's not local to this function, right? To not dwell too much on that, we check if the current is none. Obviously, it's not none. We could see the current node literally right beside it, so we transverse. Obviously, that makes sense because of going to the left. Sorry, we are with the head rather is not none. Obviously, that's why that is not none. So we go to the left, and when we step into the left, current helper at the left, so we see that our current changes to B. It becomes B, and we check if B is a none. So B is not none. We go to the left. Now when we check B, now we are going to D. So D, we check if D is none. D is not none. We go to the left. Now this is none. This current is none. So when it is none, what do? We return 0, and we could see that here. Okay, so we return none. So let's see where we are on the stack. So we see that our helper has returned 0 for the left. So for the right, it's going to also go ahead to return 0. So we see on the left it returns 0, the right has also returned 0 for the two nons on the D valued node. So we now go to the self.count, we read through it, we transverse through it, and we see self.count has been instantiated at 0. We check if current is equals to A. So basically, if it is D or E, so we could boldly see that we are already on the E on the D node D valued node. So count should increase to 1. So self.count, I don't know where it holds it, so it holds it here. You see that it increases to 1, and our total should increase as well to 1. Our total should be 1, obviously. So we see it here. Our total has been calculated to be 1, and our LCA is none. But this guy is not going to be met, as we say. Total needs to be 2, and yeah, this guy needs to be none. So LCA as none has been met, but total as 2 hasn't. So we jump over that and we return total. Now, remember, we now go back into our left. We are coming out from our left now. Our left returns 1, as we saw here. Our left returns 1. So our right, we are trying to go and see what our right will return. So which is E. It has jumped into E. Now we could see that our value has changed. Its left is none. I think its right is none. And basically, I think we could just play. Let's see if it will just take us through the entire ordeal to return back to D, because we're trying to return back to do the same stuff. I think I've jumped way too much. So basically, what happened was we went to E and we went to B, right? I wanted to show us that we got 1 here, but it went ahead to show us that we returned 2 on the left side of D, of A rather, as returned 2. But let's see that our LCA has been updated to something. So you can see here now that our LCA has been updated to a value, right? Which is what? B, because in the stack of B, as we saw here earlier, 1 and 1 was returned, and this total was met. LCA was also met as none, and then we pointed LCA to the current, which was B at the time. So right now where we are at is that the left count is equal to 2. So basically the left count of A, because we're now in the node A stack, which is the first stack we instantiated. So our left count has returned this. Let me take it slowly this time around. So we have gone into the C stack where we are going to return this. I think I will just jump again because our left is none and our right is none. So let's get to jump again. I hope it does not just take me out of the entire stuff. But let me take it slowly. Left, okay, it has returned right. So we could see that our left will be 0. This guy is not going to be met. This left and right and everything, total is going to be 0. Let's go through that. Total is going to return 0. LC has already been pointed to a node which is B, as we have earlier seen, and totally returns 0. And basically, we'll see here when we jump over that, you see left is 2, right is 2, left is 2, right is 0, self is 0. So that node, that situation is not this node. Current is none of the currents are A, so this conditional is not met. Total has 2 and 0. So when we step over, we see that the total is 2. So this guy is met, but this guy is no longer none. So LCA is already a value. So that condition is not met. So we skip over here as well, and we return total as our total value. So we see here the current is the value we passed in, which is A. So we return LCA. So our LCA would be 2, will be B, which is the lowest common ancestor, as we've seen before in brute force and also in our subsequent uh, illustrations. So even with this guy, we can step out now, and we are done. So basically, that's our debugger tool illustration of this lowest common ancestor, and we see that the function holds true and returns the value as it should. So that's it for the lowest common ancestor, brute force, optimization, and also the little caveat that was thrown where there wasn't a difference in brute force and optimization's complexity, but we could see the gross difference in real time complexity. And basically, I think that might be the highlight of this one. The first one where we see that the brute force complexity actually holds the same as the what's it called, as the optimization. So yeah, so that's it for this one. I think it was an exciting one as well. It was an eye-opening one, showing that sometimes complexity also has to, be from complexity has to be also, be envisioned. That's why we not have to understand this complexity, how it comes about, so we don't just blindly assign it and then think, oh, because this complexity holds the same, the solution is now settled. No, we have to understand where it's coming from and how to you know best understand it, and so as to know systems that work best. So that's it for this one.